Yeah, next we move on to discuss the birth, life, and death of a star, which is the main topic of interest in this lecture. Uh, there are two competing theories of formation of structure in the universe. One believes that the small objects were created first and then they combine to become the large object. The another way is to do it in the reverse, that is, the large objects are formed first, then the smaller objects condense to form the smaller ones. We believe at the moment, and this has been checked by computer simulations in an extensive way, we believe that the formation of the universe has taken place in what we call the top-down form. The top-down formation of structure in the universe is what we really believe in, which means that the bigger objects like voids and the gases, they were formed first, and then the condensation into galaxies and the condensation from galaxies into stars, etc., came later one by one. So the structures like galaxies were formed first, stars were born later, is what we believe in now. And amazingly, star formation is going on in several areas of the universe, even now. And it is interesting to see areas where star formation is still taking place. And the recent advances in infrared telescopy has increased our ability to see these areas also, because in these areas, too much light is not coming out. But the infrared telescopes are able to pick up these objects and study them. Next slide. Yeah, how does a star form and what is the material of the star? Probably many of you know the universe really consists of mainly two objects, hydrogen and helium. You're probably familiar with hydrogen gas, and you might have heard of helium also. Helium is the gas that is used usually to fill up the balloons, and then it goes up. And some of you may have heard that helium, when it is liquefied, has very unusual properties, extraordinarily unusual properties. So hydrogen and helium are the main constituents of our universe, out of which 3/4 is hydrogen and 1/4 is helium. If you're interested in going back into history, originally it was only hydrogen, or in fact not even hydrogen. The hydrogen broken up into protons and electrons and other elementary particles, which was present in the universe. But at a certain stage, before about 3 minutes or so, quarter of this became by mass helium. So by mass, 1/4 of the total content of the universe is helium, and 3/4 is hydrogen. You might ask, what about other elements? Because you all know that very important element in our own body is carbon. Where is carbon? Where is oxygen? Where is nitrogen? These elements are also there, but they are so small that we don't have to worry about them. They are much smaller than even 1%. They are very, very important for life, but they are very much smaller than 1%. So in that sense, we are starting with a mixture of gases, you can say, which is 3/4 hydrogen and 1/4 helium. Now, both these gases have gravitational attraction, so when you make them contract, then they are overcome by gravity and start contracting to form objects which are very much more dense. And when you start contracting something, or when something starts contracting, the heat starts going up. It starts heating up. And when the heat goes up, the temperature goes up, then chemical processes start taking place. And in particular, when temperature becomes large enough, nuclear reactions can start in a star. So the attraction, which would have continued, is stopped in this object, which is usually called a protostar, by the fact that the temperature goes up inside the star and the nuclear reactions start. The nuclear reactions raise the temperature even more, and at these high temperatures, that is what is called thermal pressure, as we'll see. Next slide, please. Yeah. Now, if you suppose you start with the star, which has the mass of, say, the mass of the sun. Mass of the sun is about 10⁻33 grams. So if you start with a gaseous object which is contracting and which has a mass of about 10⁻33 grams, as I said, the temperature goes up and nuclear reactions start. What do we mean by nuclear reactions? We know that helium consists of 2 protons and 2 neutrons, whereas hydrogen consists of only 1 proton. Now, the combination of 4 of these objects, now proton or a neutron can be converted into each other, and they're called nucleons. So the combinations of these 4 nucleons to form the helium is sometimes also called the alpha particle, the 4 hydrogen atoms to combine to form helium is really the fusion process which produces energy. As you probably know, we can produce energy from nuclear processes by either fusion or by fission. You can take a very big object like uranium, break it up into 2, and you get energy. Or you can take a very small object like hydrogen, combine it to form helium, and you can again get energy. The sun and most of the objects in the sky really get their energy from fusion process, that is conversion of hydrogen into helium. And how do you get the energy? You get the energy because of Einstein's relation E equal to mc squared. What really happens is the combined mass of the 4 protons is slightly greater than the total mass of the helium nucleus. And this reduction in mass is converted into energy by using this relation of Einstein E equal to mc squared. And this is the energy that is released, which is about 20 MeV per nucleon, which is what gives you the nuclear reaction and raises the temperature. Now, this process of hydrogen combining to produce helium is what powers our sun. And our sun will continue to have this fusion process and emit energy for about 10 billion years. And we should be very grateful for it, because life on Earth is possible only because of the sun and the energy that it produces. And this energy can continue for 10 billion years is really of great assurance to us that, of course, we don't know whether we will even live for 1,000 years, forget about million years and billion years, but at least we are assured that the sun will be there for billion years. An interesting point is that if the sun was very much heavier, then the sun's life would have been much smaller. So we should be grateful that the sun is not too heavy.